Hello, I'm Casey Krishnan. This is my third project for my Intro to Statistics class. Today we'll be trying to understand probability as it relates to trials. Ever do a math problem, feel completely confident in your answer, only to get something totally different? You checked, rechecked, even triple checked, but still, nope. Spoiler alert, you might not have done anything wrong. Sometimes probability just does its thing. Today we're going to talk about how that works, specifically how probability plays into the results we get when we test data. To explore how probability plays a role in data analysis, we'll use real numbers from residential home sales in Connecticut during 2020. I found a list of all the sales, about 15,000 total, from a government website. That's what we call population data. Since we had every number, we let Excel handle the heavy lifting and calculate the exact statistics. Super easy. Excel showed that the average home price for our population was $314,398.51. This is the population mean, represented by the Greek letter mu. Most homes sold for prices close to that amount, but there was definitely variation. Some houses sold for nearly $1 million. To measure how spread out the prices were, we used standard deviation represented by sigma. In this case, the standard deviation was $185,077.56. So, where does probability come in? It comes into play when we don't have access to everything. Imagine trying to gather 15,000 listings by hand with no websites and then doing all the math without Excel. Nobody has time for that. That's where probability helps us make smart, informed guesses using smaller samples. So we're going to set up an experiment. We're going to gather some samples, we're going to run some tests, and then see how likely our sample is to match what we believe is true. Let's start with our setup. Usually, the null hypothesis is our guess for what the population mean is. In the real world, we would have read some articles, did some research on recent listings, and come up with an educated guess. But that's time consuming. So luckily, we get to cheat a bit because we already have all the data and can just use that. In stats terms, we're going to say that our null hypothesis, H0, is the mean of $314,398.51, same as the population. But just the null isn't enough. We need an alternative as well. We're comparing theories to see which is the best option. So we have to choose something different for our alternative. It's like flipping coins. Both people can't call heads. Someone has to call tails. So for this experiment, even though we really want the mean to be the same as the population, especially since we know that is the correct answer, we can't actually pick that. So we're going to set our alternative hypothesis, called HA, to be the opposite and say that the mean is not $314,398.51. Okay, almost done. The final step here is choosing our significance level. That's represented by the Greek letter alpha. When we graph a curve, we're hoping our sample results land close to the true population value. We don't need it to be smack in the middle, just close enough to be believable. Alpha helps define how much wiggle room we allow before we say our guess is wrong. It sets the size of our rejection regions, these outer edges of the curve where results are considered unusual. A bigger alpha means a bigger rejection zone. How do we choose it? That depends on the risk. For serious things like medicine or safety, we want a small alpha to lower the chance of a false alarm. But for something like home sales, we can afford a little more leeway. So we'll go with the default of 0.05. Note that if my test puts the mean into one of those rejection zones, I'm saying that the null hypothesis is wrong. We don't want this. We know for a fact that the null hypothesis is correct. So rejecting that would mean we have an error. We call this a type 1 error. So that's our setup. Now we need to gather some data to use. But we have some rules to follow. It has to be random. It has to be more than 30 sales listings. And it can't be more than 5% of our population. I have a population size of a little over 15,000. So I'm going to go with 500 houses. Larger sample sizes typically lead to more accurate results. So I'm hoping this size will give us fewer errors. If I was going to get random samples in the real world, it would be a little tricky, time-consuming, and expensive. But we're not doing that here today. I have the population data already. I use some fancy Excel functions, and I get it to select 500 random samples for my population for me. Excel is awesome. So we're all set up. We've got our data. Now it's time to test it. When Excel selected my 500 samples, I had it also get our sample mean, X bar, and our sample standard deviation, S. As we can see, our sample amounts are pretty close to our population amounts. But is it close enough? Time for some math. I'm using this t-test formula. When we plug in our numbers, it gives us a t-score of 0.936. That doesn't tell us much on its own. So it's time for the next step. Check our results. Using the t-score from our calculations, we're able to find a probability value that our population mean is somewhere in this green area. Remember that we want our mean within that center area. If it was in the red area, our rejection region, we would be saying that the population mean was wrong, which is an error. Luckily, our sample data was accurate. Our results are within the desired area, and we can fail to reject our null hypothesis. Great news. But we can't do an experiment just once. We need to repeat it. I did the same test with different samples 5 times. Now, I'm not going to bore you with the math for the other 4. So, here's a table of all my results for the 5 tests. As you can see, all 5 resulted in the same outcome. Failed to reject the null hypothesis. Yay! That means none of my sample means were far enough away from the population mean to count as unusual. We didn't get a single error. That's great. But here's a twist. Getting 0 errors feels right, but is it actually what we should expect? That brings us to what this project is all about, probability. Specifically, we're trying to understand if alpha tells us how many type 1 errors we'll end up with. Time for more math. We're going to use the binomial probability formula this time. For 5 tests at a 5% alpha level, we're going to expect between 0 and 1 errors. I know that's a lot of numbers, so let's take a geeky detour. If you've ever played or heard about Dungeons & Dragons, you probably know what a d20 is. It's a 20-sided die. Rolling a 1 called Nat 1 is the worst possible roll. That's pretty much instant death. Nat 1 is like making a type 1 error in statistics. You followed all the rules, did everything right, and it still goes wrong. It's not your fault. It just happens sometimes. Rolling a 1 happens 5% of the time, or 1 in 20 rolls. That's exactly like setting alpha to 0.05. We're saying, hey, I know there's a 5% chance that I might reject the truth. So if I roll my d20 5 times, I probably won't hit a 1. But I could. That's not weird. That's just probability doing its thing. And if I roll a few 1s in a row, well, that's weird, and that die is going in dice jail. If you know, you know. So back to the project. We got 0 errors out of 5 trials. That's well within the expected range. Nothing weird here. But it made me wonder, What happens if I start changing things up? Would I get more errors if I use smaller samples? Or do I just need to increase the number of trials? First, I tried smaller sample sizes. Instead of 500 listings per sample, I used 30. Smaller sample sizes are usually less accurate, so maybe that would cause more errors. We already walked through how to do the test, so let's just jump straight to the results. Wait a minute, 0 errors again? What happened? What happened was we didn't change the probability formula. Using a smaller sample size was like rolling with a smaller die. There's still the same number of sides. We still rolled 5 times, so our chances didn't change. We need to change the number of trials. This time, we're going to do 20 tests. Before we see the results, let's see the math on how that changes the probability formula. Our new error range is between 1 and 3 errors, so the math definitely changed. But did it change in practice? Let's take a look now at what the results are. So what did I get? You can't really read that print, so I highlighted where the results told us to reject our null hypothesis. Rejecting would mean the population mean is wrong, but we know it's right because we already calculated it. So 3 rejects mean 3 errors. That's a perfect match to what our probability formula predicted. So what does this all mean? While we want a large enough sample to get accurate results, we need to keep in mind that more trials will increase our chances of errors. We still need the trials. We're not going to run just 5 tests on a new medicine that could potentially hurt people. What's important is understanding how probability works, so we don't panic every time something unexpected happens. Check the math. If it's within the expected range, then it's just probability doing what probability does. And as long as things don't get too weird, you're probably fine. Thank you.